I've been with her for 18 years, and my job title is sector specialist, which really is technical support to the sales team. I will be joined virtually by my colleague Casey. We have a video recording, a recording of her demonstrating the IntelliCIP platform, which is what I'm going to be talking about today. So today's agenda. Why do CIP parameters need to be validated? What data can you get? And making data-driven optimization decisions using IntelliCIP. So why do we need to validate our CIP parameters? Well, thorough cleaning is obviously a crucial prerequisite to achieving sound hygienic conditions in any food manufacturing, whether it's beverage, whether it's food, anything with CIP, it needs to be cleaned properly. Currently, let's just say validation can be variable. For a lot of people, it's taken for granted. Some people, you ask them, have their CIP sets been validated? And they go, well, we think so. But if you think about it, it is now mandatory for most global food companies to have the validation in their quality system. And indeed, it's included in the new BRC version 9. It's in the IFC food version. It's in the FFC 22000 as a standard. It is part of their process validation. So performance of process validation using the collected data is relevant to the product safety and the process, and you need to revalidate if necessary. So in practice, this is actually a good opportunity to look at what you already have, because quite often CIP systems are running on their original commissioning parameters. And as we all know, when things are commissioned, they are tending to make sure they pass the acceptance criteria rather than being efficient. So they're effective, but may not be efficient. But also to relook at it to make sure that you're reducing your risk of product contamination and all of the consequences, whether it's product recalls, damage to the brand, loss of market share. And it's an area to identify those critical areas and opportunities for optimization within the cleaning program. If you don't look at it, you won't, if you don't measure it, you don't manage it, basically. So there is national and international legislation that requires food industry to ensure that food placed on the market is safe. EC 178/2002 states that products should not be injurious to health or unfit for human consumption, whilst the machinery directive requires that equipment manufacturers should provide cleanable equipment. And also it's in all of these external accreditation. So cleaning is seen as an integrated part of a production system. And if you think about the new BRC version 9, it includes the following phrases. Validation confirming the correct design of the operating system is within the BRC. All CIP equipment shall be designed and constructed to ensure effective operation. And also the fact that limits of acceptable and unacceptable performance for key parameters shall be defined to ensure the removal of target hazards. So that at a minimum, these parameters shall include times for each stage, detergent concentrations, flow rates, pressures, temperatures. And these shall be validated and records of the validation maintained. Now that's within BRC version 9. So how does validation marry up to everything else? Well, validation is only one part of the three-step approach to cleaning. So you have validation, verification, and monitoring. After the cleaning validation itself, which is the first step, we should obtain an outcome which will typically give directions for setting up of the verification and monitoring program. Both verification and monitoring are taking place after cleaning validation. and they confirm that the cleaning protocols are being adhered to and operating as intended. Monitoring and verification programs should be appropriately and properly implemented to ensure that the validated cleaning programs are followed and operated as they were when they were validated. All three concepts are actually quite commonly confused, so it's important to clarify the differences. So, validation is any action providing and documenting that a process, procedure, or method actually and consistently leads to the expected results, and thus meets the cleaning objective of hazard control. So you obtain evidence that the control measures are managed by the hazard plan and by operational prerequisites are capable of being effective. It's an assessment prior to starting operations. It's confirmation through objective evidence that the specified requirements have been fulfilled. Verification is confirmation through the provision of objective evidence that specified requirements have been fulfilled. And that's carried out after the operation, during and after operations. And monitoring is the activity undertaken during operations. So it's conducted a planned sequence of observations or measurements to assess whether control measures are operating as expected. So you must really validate the effectiveness of your operational prerequisite programs and critical control points before ending the before that food safety management system is changed. So validation, generally speaking, is a combination of tools which are used to ensure that the total food safety management system is working and to evaluate the food safety data before a food product is released, either through internal or external results. Now, obviously, these three concepts are linked. So validation is, does it work? Monitoring, is it working? And verification, does it work? That's a sort of an easy way of remembering it. So once a cleaning procedure has been validated, it should be routinely applied, and the process should be monitored and verified. Now, revalidation may be required when there's any changes to equipment, manufacturing process, or even cleaning procedures. In terms of monitoring, is it working? You monitor the effectiveness of the cleaning performed during every cleaning procedure. So it includes planned sequence of observations, measurements, records, and documents of control parameters. Monitoring activities are typically real time, and they're measured during cleaning. And verification, has it worked? We need to determine that the control parameters have been implemented as intended. So it takes place during or after the cleaning procedure through a variety of activities, like review of records, to confirm that the implementation of the control parameters matches the specification. So now, cleaning validation can be prospective. Prospective means that it's completed before you've actually produced anything. And you check to see the cleaning procedures will be capable of obtaining the results that you require. It's the sort of initial validation. The concurrent clean validation is happens simultaneously during production, and you're trying to make sure that the results that you're expecting to get are being got. And finally, retrospective. This is based on analysis of historical data to provide documentary evidence that the cleaning protocol is effective. And normally your retrospective is something that you've had all the time. The prospective is when you're looking at new equipment that you're going to be bringing in to check to see how you can clean it effective. And the concurrent is when you're producing, when you're using it. So validation should be a standard procedure, executable on an existing facility and equipment of any different age just to improve the general hygiene level. So it should be object-based, it should be repeatable, and it should be standardized. And the results should be reasonably fast and to provide an actionable output. So what data can you get from your CIP system? A well-designed CIP set has lots of valuable data. So from your sensors, you have flow, temperature, pressure, conductivity, turbidity, pH, redox, any of the sensors that you have on your CIP set. Of course, not every CIP set will have every type of sensor. And it's important to note that if the data is available, how are you actually using it to benefit, improve, or validate the specifications of your CIP set? I mean, in general, most people have flow, temperature, and conductivity, but what do you actually do with it? From the PLC, you will get the recipes, object information, alarms, valve feedback, process interlocks, all the things like that. But what do you actually do with it? Now, some CIP sets, and not all, are equipped with a data logger, but you cannot easily generate reports from it. It gives you the data, but in some instances, that data is only available when the cleaner is going on. As soon as the cleaner is finished, that data is lost for the older ones. Some CIP systems will output, say, a PDF of the cleaning run graph and the main data to say how long everything took. But it's that's all you get, the graph. Some systems can export data to see some files, but they all have slightly different formats, making processing and evaluating complicated. We've not seen any CIP system in itself that can run statistical analysis of the cleaning data. I will now like to do a video of the demonstration of IntelliCIP and how that operates to take all of the information from your CIP set and make it into a very useful tool, both for conformance, for verification and compliance, but also for operational improvement. So if you excuse me 2 minutes, 1 second, I will put the video on and
Our objective with today's first IntelliCIP demo is to provide a general overview of the example of how to use the tool to make mistakes. Within the platform, there is a built-in help document that provides additional information and guidance for each icon and its function. Let's first take a quick view of how the data is initially processed and organized before we jump into the details. The platform is organized into 2 tabs, the Overview tab and the Compliance tab. By viewing the Compliance tab first, we can see how the system organizes the data received from your CIP PLC. First, the system records each CIP run automatically. As a user, you can choose which CIP run to review. The cleaning run list has information about when the run has happened, where it circulated, what it cleaned, and how it performed. Each cleaning run's performance is indicated with a traffic light system. The green circle indicates that the cleaning was evaluated and met the compliance duration for each parameter for both hygiene and cost risks. This red circle indicates a hygiene risk. The system is identifying that 1 or more of the cleaning thresholds are not meeting the minimum compliance duration times for conductivity, flow, or temperature. The second area we focus on is efficiency opportunity or cost risk. The yellow circle indicates to the user an overuse or overcleaning. We would see a yellow circle if, for example, the conductivity is remaining high for a longer period than is necessary. We can see that a recipe with a consistent finding can indicate an opportunity to reduce water and energy costs. To summarize, the yellow circles may indicate recipes that consistently overperform. If there is no flag, then this indicates that no comparison was made because no data is available in the recipe. Now that we understand how the data arrives in the system, we start with the overview. The overview tab is like a cockpit for the CIP unit on site. A quality or plant manager can view compliance, consumption usage, cost, and the number of hours spent on CIP cleanings for his or her plant. At a corporate level, a user can view each plant's success or areas to improve in one location. A user can view the summary data based on a filter selection to narrow the focus of the data. As you can see at the top of the page, the user can filter and drill the summary information based on CIP unit, line, circuit, recipe, and time period. If we select a specific time period, the data displayed only falls within the date range. By selecting the time period, then custom range, and then April 1st through April 30th, 2021, now the data displayed reflects the month of April 2021. The information can be expanded or narrowed in. There are two live tiles. By selecting the consumption tile, a user can see the details behind the consumption of their CIP runs. The consumption indicates the average consumption per clean for the month of April. We use the average to make it easier to compare from period to period. Let's scroll down to see the daily consumption for the selected period. For example, we can see in the bar chart the daily consumption of water. Scroll back up and select the compliance tile. We can now view when the compliance risks occurred and by the type of risk, hygiene or cost. In this case, we can see there are 42% of cost issues during the month of April. Scroll back down to see the number of occurrences of compliance issues each day. By clicking on hygiene or cost, you can see when the occurrences happened for each category. Scrolling back up to see all of these issues in the month of April, let's click on the link, Show All Issues, to view the issues in the Compliance tab. The Compliance tab gives all the details behind each cleaning, answering when, where, what, and how it performed, streamlining and highlighting areas with potential opportunities. Because we use the link from the Overview tab, the system is loading and the data will show shortly, sorted automatically based on performance and the beginning date. Scroll to the right, you can see the performance and consumption details of each clean. Now let's click on the cleaning to take a closer look at how the system helps us dive deeper into the details. Scroll down to the compliance report. We can take a closer look at the report and learn which steps had a fail in the respective risk, hygiene, and or efficiency. What you can expect is that the system will separate phases within the CIP. We can clearly identify when the pre-rinse is happening, the caustic step, and so on. Within each step, the parameters that are available within the CIP are viewable in the compliance report. There is a column that indicates if the sensor data is in the forward or return position. There is a column that shows the parameter requirements and target compliance duration. The final two columns labeled hygiene and efficiency have a pass or fail to indicate that what is happening during the CIP clean is within the agreed threshold durations. The report can be exported as a PDF for easy email attachment and archival. The report combines the information from the cleaning run list, cleaning graph, and compliance report. And here it is. Now let's get back to the compliance report. For each phase, compliance is calculated and separately for all the measurements that have parameters. Only the hygiene parameters are included in the report, as the compliant time is calculated based on hygiene. The expectation, or what is indicated as fail, is based on the time. Efficiency compliance is currently only based on total time duration. From this report, we can see that the caustic phase is compliant. Let's look at the details for the acid phase. The minimum flow is 25 cubic meters for a target duration of 8 minutes and 30 seconds to 14 minutes. The flow meets its target for 11 minutes and 49 seconds. Therefore, it passes. The conductivity only met for a shorter duration than the target time, and we see the fail. In the final rinse, the temperature meets the target for longer than expected. Here we can say that more energy, more water, and more time is being used than necessary. This could be a potential area of improvement from a hygiene or efficiency perspective. Now, let's take a look at the signal graph. To see the behavior of the flow, temperature, and conductivity during the CIP cleaning, we look at the measured sensor data in the graph. As the information is coming in, the system allows for a CIP event to be broken down into phase events. Above the graph, there are class bars for compliance. Green means compliant and gray means non-compliant. Class bar directly above the graph is the main compliance, and it is only green if all individual parameters are compliant. As we move above the total compliance bar, the additional class bars match their signal colors when compliant, and again gray indicating non-compliance. The signal legend allows a user to select which signals to view, and the toolbar with various zoom and cursor selections to see exactly when the parameter is out of compliance. There are many neat features that are built into the signal graph. For example, the zoom tools, the ability to view one signal at a time, or adding cursors to enable you to extract information. The compliance report directs a user where to look, and the signal graph provides additional clues to explain the behavior. Below the graph, we can see what the CIP station cleaning run activities are. The colored bands show what is happening in other lines of the CIP. The line occupancy also indicates if there are issues in the cleaning phases. There's also a line for the CIP unit that gives a 24-hour overview. There are two remaining sections that I haven't shown yet. That is the recipe table and the statistics graph. The recipe table shows what an average run of the particular circuit and recipe combination looks like. As a user of this powerful platform, you can now compare the stability of one recipe to the next. I won't go into too much detail as we will be going through an example shortly. Using the statistics graph and recipe table, we can learn the average duration and average compliant duration for the whole cleaning and the individual phases. We can view and sort the number of compliant and non-compliant recipes. We use the global filters to further filter the data we use in the graph. For example, filter a specific recipe within that original time period. This demonstration is showing you a top-level view of how the system works.
Right, let's share again. Right, so that has, as you can see, the IntelliCIP system checks each clean against agreed parameters, and those parameters are set up in agreement with yourselves and ourselves about what is important. And therefore, you've got your monitoring and verification requirement already done automatically. Now, I know there are other packages out there that can do this. They look at the clean and go whether it's met your standard parameters, but I'm not aware of any that go to talk about anything other than hygiene. This package talks about efficiency as well, saying most packages will say if we're aiming for 60 degrees on your clean, if it's above 60 degrees for the time stated, everything's fine. The fact you're cleaning at 90 doesn't matter, but this will be highlighting the fact that you're overusing energy, overusing water, overusing chemical. So it's more, but it is more than remote monitoring and visualization of the sensor data, because it hones down into the individual clean, but also compares each clean to itself. Okay, and it can reveal some very interesting stuff. So we have your monitoring and verification ticked off. Let's look about operational improvements. So how you can make optimization decisions using the data that you get from IntelliCip. So everyone assumes that all automated CIP runs are exactly the same. And that really doesn't happen in real life. And we can show that because this is a case study, some examples from a beverage site, which will remain nameless. But we analyzed the cleaning of 11 syrup tanks. And so we compared 971 cleaning runs, all with a standard 5-step CIP program. So it did a water rinse, it did a caustic circulation, 75 degrees C for 15 minutes at 15 cubic meters an hour. Then there was an intermediate rinse and a hot water sterilization, 85 degrees for 10 minutes, and then a final rinse to cool down. And this is distribution of all cleaning runs by duration. So obviously, there are some outliers. Okay, they will be aborted cleans, or it's gone into alarm and the alarm has held for a long time while they were sorting out problems. But if you look at the standard deviation of the data population, it's, as in the plus or minus one sigma, the duration is 22.28 minutes, which is almost the same as the required compliant time, as in the variation in the clean is almost the same as the actual total cleaning time. So that's the 15 minutes caustic and the 10 minutes hot water sanitation. Which again is almost the same as the time that you should be optimally cleaning for. So let's have a look at the actual distribution of those cleaning times. So this is a scatter graph of the compliant duration. So 25 minutes is there. We have under clean, but we have significant numbers of over clean. They're compliant, but they are taking you longer than you require. So is that 25 minutes guaranteed? Will we always get that? Well, we will see on the next slide. So the distribution of the caustic step. The validated target parameter for the caustic step is 15 minutes. You can see, again, we have some that are under clean. Now, obviously, the ones with very slow, very low will be where they've been aborted or that. But there are some which are close to 15 minutes, but still not 15 minutes. How does that happen if the PLC is supposed to be able to continue it? Is it that people are skipping things? Are they stepping on? The majority of them are compliant, but for longer than 15 minutes. There are steps that are over 25 minutes. So, you are cleaning for longer than you should. Your hot water distribution. Again, we have the majority is over clean but compliant. So a lot, the non is much bigger. There are many more under cleans than there was on the hot water than there was on the caustic phase. So it's actually almost 5% of the cleans were under the 10 minutes hot water. And this, again, is the caustic compliant duration, the total caustic step duration. As you can see, there are failed for whatever reason. There is or rather there are some with 21 minutes of caustic. So it's very near to the optimal run. So it proves that you can do this. This is the same clean every time. We're looking at the same type of clean with the same objects. It can be done every time. However, the majority are above this. And there are some massive outliers. Now, okay, some may be alarms that cause it to be for too long, but why have we got such a big scatter? And because we are talking about the same object, there's no reason why we should have such large scatter. So here should be our optimal time, because we realize that when you start the caustic and end the caustic, it'll take a little time to come in and out. So it proves that it is possible, it has been done. And with this type of statistical analysis, you can hone in on the cleans that have the most variability, which means that you can focus on the areas that you need to focus on first. So you can say that the cleaning runs are compliant to the recipes. They're satisfying the validation parameters, as in the majority of them are getting their 20 minutes or 15 minutes of hot caustic, but a lot of them are getting significantly more. And the compliant runs show that there is a variance that is larger than should be accepted. Now, the caustic is more compliant than the hot water. But why is that? We can look, it gives us the tools to say we need to focus on the hot water to find out what's changed, what's going on, why are we not achieving it all the time. So how can we say there is an ideal CIP when the optimal run is not the one that we're expecting? Because an optimal CIP run should satisfy both the hygiene compliance parameters, but at the lowest possible cost within the capabilities of the automation system and with the acceptable variance that you can get with it. Because as we said before, those graphs are from the same CIP set, cleaning the same objects, but we're comparing 971 cleans with each other. And that's why you can see the differences. If you're just looking at one clean, whether it's compliant or not, you will see yes or no, it's compliant. But you won't see the scatter. And what can we do with that? Well, obviously, once you analyze the program, you then identify the processes with the highest variance, you investigate the reasons for the variance, and you may or may not modify the program to try to reduce the variance. And once you've done that, you evaluate the new program performance, and either you accept it or you go, well, that change didn't change anything. Let's do it again. Let's find out what it could be. So it's all part of that circular management cycle of change. And that compliance versus total time monitoring can be really useful to make sure that the CIPs are operating at their expected validated parameters. And obviously, the larger the data set, the more data-driven optimization decisions can be evaluated and implemented. So the longer you do this, the better the data you get, and the more information that you can drill down, the more benefit you can get. Because the idea is to get your most effective clean in the most efficient time. So that's all about IntelliCIP. We have 10 minutes worth of questions if people would like. Obviously, IntelliCIP, we do offer other things, but obviously this presentation is about IntelliCIP. So any questions?
I've got a question, Paddy.
Yes, Ruth.
Yeah, so what size facility does your system work with? I mean, what size of brewery or drinks manufacturer tends to be, you know, the affordability?
The affordability, it's less the affordability because there's an installation cost and there is a process the data, and obviously that fee changes whether you're doing 100,000 cleans or 10 cleans. It's for me, it's more, do they have the sensor set? Because IntelliCIP will only give you what the answers to what you already have. Okay, so if you do not have a flow meter, you cannot give any data on flow because you don't have it. It's a standard. It is something that uses the data that you already have, uses it. And so if it's a small sort of people without the requisite IT, so that it's a manual CIP set that people press buttons, it's not appropriate because you don't get that automatic. So it needs the level of automation to be able to automatically get the data to then crunch it. So if you don't have that automation, it won't be appropriate.
So what sort of also, how can a small on the journey towards this ideal?
That would be that they would have to invest in the infrastructure to actually achieve, because if you don't have the flow meters, you don't know whether you are meeting the required flow for cleaning properly. If you don't have a conductivity meter, you are not constantly monitoring your caustic strength. If you don't have a temperature probe, how do you know if you're meant to be cleaning hot? How do you know you are cleaning hot?
Yeah.
So you need to have that baseline information before you can start. And obviously, if you have those sensors, you need something to control them. So you now have a PLC system. And once you have a PLC system, you can implement this.
Yeah.
If you have just, someone presses a button to start, someone presses a button to stop, then yeah, this is no use.
Okay. Paddy, I can't see your email address on there, but there we go. Thank you. So if anybody wants to contact you, that's that. I can't see any questions coming in. So that being the case, we will close it. Oh, hang on, we've got a question. Eddie. Yes, so Eddie Gadd's just asking a question, who says, yeah, slightly beyond his reach at the moment, but very interesting nevertheless. And that's what I'm seeing. What, the theory of it and everything is what everybody should be doing. And I think it's that process and that pathway towards. It's very interesting.
You need to have the data first. If you don't have the data, you can't analyze it.
Yeah, which is a no-brainer. But again, it's putting the equipment in, etc., to be able to do that.
Yes. Yeah.
Yeah.
And it is. I mean, I go to places where, as I said, that they have the information, but as soon as the clean stops, it's lost.
Yeah.
So how do you know that clean was effective? Now, admittedly, those are the sort of the older or the smaller places, but unfortunately, if you want to comply, you need to do something about it. You need to, otherwise, how are you going to achieve your BRC standards version 9? Which does state specifically you need to check as a minimum your flow, your temperature, your conductivity.
Yeah, I mean, for me, sorry.
How do you prove that?
Yeah. For me also, it looks like it's an issue of have you been able to work out over the years how much water and energy a facility has been able to save because they've been able to work towards optimizing their CIP?
We do. Yes, we have studies which show if you have, as I said at the start, most people's validations are done by the OEM, and the OEM wants to get paid. And they get paid on their acceptance criteria, and therefore they ensure that the CIP set is set up with parameters that will ensure that they pass the acceptance criteria. So it's effective. No way are they normally efficient. And therefore, by going in and optimizing the CIP set, you can save significant quantities of water and energy and time.
Yeah.
and time often is more is of more value than the water and effluent. Now, I know for environmentally we want to reduce water and effluent, and yes, there's a cost, but normally, you know, a cubic meter of water in and out is say £2-3. So you save people 10 cubic meters, you save them 30 quid. You save them an hour, that's worth £1,000–1,500. So quite often it's the time that is the biggest value than the other stuff. But it all adds up and it all counts.
Lovely. Okay, well, thank you very much, Paddy. And we can all now go off to our working day full of knowledge, and thank you. And thank you everybody for attending.
Thank you very much.